So I'm going to talk about this string analysis work that I have done with 3 PhD students now. 2 of them finished their PhDs. I have one slide of marketing, okay? All the papers we wrote, I think the most recent one is, yeah, we have another one actually. They just got accepted, but I couldn't have time. but so anyway, so we wrote a bunch of papers starting in 2008. This was our first paper in SPIN, software model checking. We published in some verification conferences like TACAS, CAV, but we also published some stuff in ASC, ICSI, ISTA, so more software engineering oriented publications too. But I want to mention 2 things. I had 2 PhD students graduate on this, and one of them got our department's outstanding dissertation award. That's Fang Yu. He's tenured now. He's in Taiwan. Another one graduated in 2014, and he got the ACM 6 Outstanding Dissertation Award. So I'm very proud of him. And he's now a faculty member at. He's from Saudi Arabia. He went back there, and he's an assistant professor there. So so this 2 dissertations of work. So I can't go over all the details of all the stuff we have done here. So I'll just mention some work from this line of work, and they're all, I guess, under the title of string analysis. So here's my very brief outline. I'll have some motivation. I'll talk about the symbolic string analysis and some automated repair. And I had a meeting with with some of researchers from this group, and Lionel and Domenico and then Shah, and then I learned that you know most of this stuff already. So for some of you, it's going to be repetition of the stuff you know, but maybe some of you, it's going to be new. And then I'll talk about this automated repair work too. So, we are interested in analyzing strings, string manipulating programs. There could be many motivations for these. I'm going to focus on one of them, and that's related to vulnerability analysis. And the strings are used in input validation and sanitization. String manipulation is used there. So that's the problem I'm going to focus on. But there are other areas that you can use strings, like for example, again, database query generation, and you want to make sure the queries you generate for databases are in correct format, and so that's string manipulation. You generate formatted data, right? XML format. You want to check that the format is correct, or you dynamically generate code, like JavaScript code, and you want to make sure that the code you generate is correctly generated. My interest in string analysis has been more in the security domain. So let me just briefly go over, what part of security. We are doing web application security mainly. And so how does a web application work? Well, there is a user submits some form, on the client machine, and there is some client code that's executed when the form is submitted, right? So this is your interaction with the browser. And there's some code executed there already. And then some request is generated, and that's going to send to the server through the internet. And then the web application server receives this request, and it executes some code that possibly interacts with some database, and then constructs a response, and it gets back to the user, and then that page is viewed in the browser. So that's typically how your web application works. Now the thing is, how do you give your input to the web application? And it's typically in string form. So you type something, and then, for example, here it's asking you to create a password, some application, and it has some constraints on what a password is, right? So it says, well, you should maybe use 7 to 16 characters, do not include coming words or names, combine uppercase letters, lowercase letters, numbers, and symbols, or whatever. And then based on what you submit, actually the application may reject it, and it may say this is not a good password, right? So the application has some rules about what is an acceptable input, okay? So where are these rules checked? Whenever you submit, in this case, this person is submitting an email address, so that application on the client side using some JavaScript code may check actually if the input is a valid email address, right? So some input validation can be done there. Also, it may check on the server side. So of course you may say, well, if you are checking on the client side, why are you also checking on the server side? Well, because actually you can't trust the client side, because client side code can be bypassed because this person could be a malicious user. So therefore you may want to also recheck it in the server side. But so this is some input validation is necessary on both ends of the application typically. Now, if this was just input format checking, it will still be an interesting problem, but there is an even more serious problem, which is the vulnerability analysis, where the user is not, we are not only concerned about the user providing inputs that are not in the correct format, but the user may be a malicious user and actually try to do something bad, okay? So there are many examples of this. SQL injection and cross-site scripting are the most famous ones. For example, SQL injection is where a user, a malicious user, tries to execute some SQL commands in the backend database by submitting an input that actually contains an SQL command in it. So SQL injection attacks, right? In cross-site scripting, the malicious user provides some input for, so let's say, for example, for a blog post, right? Types some input, and then when that blog post is actually viewed by another user, the blog post contains some script in it, and that script gets executed in another user's computer. So that's cross-site scripting. So, and these are the things we don't want to happen. We don't want the malicious user, executing things on the machines that they shouldn't have access to. So, and this we want to figure out when the user submits the input that this doesn't happen, right? All right. Okay. So now these type of vulnerabilities are actually very significant, and I have two types of data to show that. One is as a percentage of all computer security vulnerabilities, how common are these vulnerabilities? Okay, so this graph is showing this. So there is this CV repository where people collect all the computer security vulnerabilities. As you see, starting from 2000, when web applications are becoming increasingly popular and people don't know how to build them, okay? So we see increasing vulnerabilities, all right? So because people are not familiar with vulnerabilities in web applications, they're just developing web applications, it's a new area. So then we see some decrease, in web application vulnerabilities of this type. But then it's still 15% of all security vulnerabilities are web application security vulnerabilities that relate to this input validation and sanitization. So this is pretty common, right? Moreover, if you look at just web application vulnerabilities, actually we see that injection flaws or cross-site scripting are always in top 3 in the last several years. So these are, if you are doing web application security, these are the type of vulnerabilities that you want to worry about. Okay, so now I have this little example of web application vulnerability. So this is about a mom. If you probably have seen it before, I don't know, maybe you not. So this mom is receiving a call from the school, her son's school, and this is the principal saying, "Hi, this is your son's school. We are having some computer trouble." And then she says, "Oh dear, did he break something?" And then the principal, "Yeah, in a way, he did break." So then the principal says, "Did you really name your son Robert single quote, right paren, semicolon, drop table students, semicolon, dash dash?" And then she says, "Oh yeah, little Bobby Tables we call him, that's his name." Huh? So then the principal says, "Well, we have lost this year's student records. I hope you are happy." And then the mom says, "Well, I hope you've learned to sanitize your inputs." So now, how did this vulnerability happen? Let's look at the code at the school. So the school has some code. I'm showing PHP. Some PHP code where they get the name of a student from the web application. Some maybe teacher enters the student name, and then they generate a database query to their student records where they use the name field, the input from that the teacher entered, as the name of the student, and then they send this the query to the database. Now, if we enter Bobby Table's name as the name variable there, okay, which is his name, this actually ends up creating a different query than what was intended, because what happens is this query, select query that's being sent to the database, is terminated with the semicolon, and the name is Robert. But after that query, there is another query which is drop table. So this is the query injection, right? So this user basically injected a new query to the query that was being generated, and then that deleted the student records, right? So we don't want this. So what's the moral of the story? We have to sanitize the user input. We have to check the user input. Now I will use another as simple, again, code example as a running example. So this is a different, let's say, cross-site scripting. One thing I want to point out is that for this type of SQL injection vulnerability, this database query operation is the sensitive operation. So we call these sinks. So the operations that are crucial in terms of vulnerability that we are analyzing. So for some other vulnerability, let's say cross-site scripting, it could be an other function, right? So these are the functions that are sensitive and we need to analyze them. So for this example, that another simple piece of code, I have an echo statement, and if I'm doing cross-site scripting, that's the sensitive function. So I'm interested in like what kind of strings reach to this echo function. And so this piece of code, it gets again some user input, some constant string, concatenates them. The dot is the concatenation operation, right? And then this user variable, user input gets assigned to that variable. It's used there. And this echo function basically uses a bunch of, generates the string. Now, this contains a cross-site scripting vulnerability. Why? Because I can insert some code to this string, and that's not good, okay? So, for example, I can have some input. Sorry, I realize I have to get my time, so I see how I'm doing on time. All right. So for example, I can get a user input that contains an executable script, okay? And that will get assigned to this variable. And then that will flow into this sensitive function. And now I have this cross-site scripting vulnerability. So what did people do? People do taint analysis. So security people figured out this problem, and they also have a technique called taint analysis to solve this. So what do they say? The user input is tainted, meaning that user input can contain bad things. I don't want bad things to reach to sensitive functions. So they do a dependency analysis. So user input is tainted. It's assigned to this variable. Now that variable is tainted. That variable reaches this expression, which goes to a sensitive function. So that's tainted. So therefore, there's a vulnerability. All right. Now, they report this vulnerability, and the application developer says, oh, I need to sanitize my input then. All right, so puts a sanitization statement. So now this sanitization statement is a replace statement that, according to its semantics, replaces anything that does not match this regular expression here. This not match is coming from that. That's the negation. And then there's a regular expression here. Anything that doesn't match that is replaced with this expression, which is empty string, okay? So it takes this variable as input. In that string, anything that doesn't match this pattern is replaced with empty string, and then it assigns that. So basically, it deletes everything that's not good. So it's kind of a whitelist approach. It says, these are the things that are good, delete everything that doesn't match it, all right? So this is called sanitization. So then, since I sanitized my input, so now if I do taint analysis, I say, okay, it was tainted. Now it's tainted here, but now it's sanitized. It's cleaned, so it's not tainted anymore. And that flows into that, so now it's safe. It's not vulnerable. And this statement I'm showing you is from an application, actually, in some web application, open source web application. So now let's run this program on this input. Let's see what happens. I'm not running. I'm showing you simulated. So if you pass this script input to this, it will come here. It will come here. And then when it goes through this script should be deleted, but it's not deleted. Actually, it flows through. So this sanitization function does not clean it, does not clean the string. So now what is going on? Because there's a bug, okay? There's a bug in this replace function. And the bug is right here. You see this dash? Dash has a special meaning. It means all the characters between A and Z. For example, when I say A-Z, all the characters between A and Z in the ASCII encoding, okay? And dash, dash, use the dash here. But here, what the developer meant was dot, dash, and at symbol. He didn't mean to use dash as a range here. Actually wanted to say just dash is okay, okay? But forgot to escape the dash. So you need to escape the dash. So you need to put the escape symbol there and say that now I mean dash, not the range. So since the developer forgot to escape the dash, then actually this left angle that they wanted to delete, which actually causes the, if you didn't allow left angle, then you would be safe with respect to cross-site scripting. That left angle fell through, and then, so then you have a vulnerability again. So the point here is that taint analysis doesn't solve this problem. Okay, so you can't solve this problem with taint analysis. You need to analyze this string expression. And it's a complex expression, and you need to understand what it's doing. So, so I'll talk about some techniques we developed to solve this problem. So at the high level, what I'm going to talk about is that we have some sinks, sensitive functions that I'll call sinks. We have some user input. And then we want to make sure that whatever the user input is, when I come to a sink, the set of strings that come to a sensitive function, to a sink, is safe with respect to some attack. Now the question is, well, what is the attack? Well, people developed attack patterns to characterize different attacks. So this particular regular expression you see here, where I mean sigma, I mean any alphabet symbol, sigma star, I mean clean closure of that. So any string here that has left angle script as a substring, that's what this attack pattern means. I want any string that matches this should not reach the sensitive function, all right? Should not reach a sink. So this could be my characterization of correctness, right? And if you violate this, you have a vulnerability. So now notice that this thing is a little bit trickier than it looks, because you may say, well, just use this attack pattern at the input, right? So make sure that no input matches this, so solve the problem. And it doesn't solve the problem. Here is an input, left angle, bang, SREP plus, whatever. And this input does not match the attack pattern, okay? It doesn't, right? So attack pattern says, left. So this input doesn't match the attack pattern. If we run this input through this application, and it comes here, the faulty replace sanitization function will convert it to an attack, actually, although it's not initially an attack, by deleting those extra symbols that I inserted. And actually, it is vulnerable still. Of course, I need to be very clever and know what is going on in your application, but an attack is possible. All right, so just using the attack pattern in the input doesn't work. All right. Actually, there is a name for the inputs that can cause a vulnerability, and the set of inputs that can cause a vulnerability. That's called a vulnerability signature. It's different than the attack pattern. Attack pattern are the bad strings at the sink, whereas vulnerability signature is the set of strings that might cause a vulnerability at the sink, okay? Input strings. And for the little example I showed you, the vulnerability signature is this, I wrote an expression here, which is hard to read, but basically what it says is that, you take the attack pattern and you can insert a bunch of characters that are deleted by the sanitization function anywhere you want, and those would be fine. That's your vulnerability signature. Any input that matches this is potentially an attack, and that is different than the attack pattern. So this is called vulnerability signature. All right. So now I'll talk to you about how we detect vulnerabilities and how we generate this vulnerability signature, which is what we do. So we use automata-based string analysis, and some of you are familiar with it, as I learned today. So we generate automata that characterize values of string expressions. Okay, automata is well known, right? Automata are used for characterizing sets of strings. So that's what we do. We have a program analysis techniques which construct automata for characterizing all possible values of string expressions in a program. All right. So how do we do this? We have, I'll show you on an example. We have two phases: a forward analysis phase followed by a backward analysis phase. So we go through the control flow graph or the dependency graph, forward and then a backward pass, and then we generate both the test if the application is vulnerable, and if the application is vulnerable, we also generate the vulnerability signature, a characterization of all inputs that can violate the, that can cause a vulnerability. So I had this small example, so I'll show you what we do. So from this little example, we generate the dependency graph. So in this version, I'm showing you, for example, there are variations of this technique. So in the first version we implemented it, we did it pet insensitive. So branch conditions were ignored, all right? We have a pet sensitive version of it too. So if the branches are on string expressions, we can also handle that. But so you can have different variations. So in the most basic version, you just generate a dependency graph for your application. Dependency graph shows you have some sinks, sensitive functions, in this case echo, and you have user inputs. And the dependency graph is showing you how values of user input or string constants flow into this sensitive function, okay? So you have string operations like, for example, concat, replace, so you can have all sorts of operations, right? So now, what our goal is, take this dependency graph and annotate it with automata. So each node in the dependency graph will get an automaton characterizing the set of strings that can reach there. All right. So I'll show on an example, and then I'll go back to point. So for example, if there are some constant strings like this URL, it's a constant string. I know that it's very easy that I can construct an automaton that accepts that string. So that's what I say. I'm not showing the automaton. I'm just giving a regular expression for you, but I can construct an automaton for that regular expression. Here is another. This is a regular expression, and I construct an automaton for that. Now, user input, I'll say, it's a little bit hard to see. I should have used a bigger font. But user input, I'll say sigma star. So any string, OK? So now, when I see an assignment, I'll propagate that. So, well, if this is a sigma star, then when I assign it to a variable, the set of values for that variable is also sigma star. Now, the interesting thing is what happens when I have a replace function. So now this is called post image, computing the post image or whatever. So I need to compute, given the automata for all the arguments of the replace function, I need to construct an automaton for the output of the replace function. So we have a paper on that, and then we construct the automaton that accepts all possible values for the output of the replace function. Concatenation, then we have concatenation. Well, the concatenation is well known in automata theory books. Given two automata, you can construct an automaton for the concatenation language. So we do that, construct concatenation automata. And at the very end, we get an automaton that characterizes all string values that reach the sink. So now all I have to do is take the attack pattern, which itself is a regular expression, see if the language intersection between the set of strings that reach here and the attack pattern is empty or not. If it's not empty, in this case it's not, then I know there's a vulnerability. Okay? Now I showed you regular expressions, but in the implementation we actually construct automata. So here is the automata that is constructed that corresponds to this regular expression with our tool. Now this automata is a little bit strange. You see that I have all these bits stuff. That's the encoding of the alphabet. Okay, and actually this automaton is a symbolic automaton. We use Mona package, automata package, developed some time ago by Niels Klarlund and Anders Moller. It uses BDDs to encode automata. So this is a symbolic automata representation. Just to give you a very high level idea, if you have an automaton is a graph, right? You have edges. For each node, if it's a DFA, which we do use DFA representation, from each node you will have one transition for each alphabet symbol, all right? So if your alphabet is big, you will have a lot of transitions. Now this automata encoding we use actually encodes the transitions of the automata using a BDD, a binary decision diagram. Now, if you don't know what a binary decision diagram is, it's like, it's not a very complicated data structure. It's actually, for each node, you order the bits. If you have a set of bits, like in this case, we are encoding the alphabet of the automaton as a bit sequence. So we assign a set of bits for each alphabet symbol, a unique, set of bits for each alphabet symbol. And this is like the BDD is like a graph that tells you when you see a bit, if its value is 1, it says go this way. If its value is 0, go this way. So in this example, I'm using the solid lines to indicate 1, and I think dashed lines to indicate 0. So for example, here in this node, if bit 1 is 1, go here. If bit 1 is 0, go there. So now how does this encode this automaton? Well, in state 0, if I'm in state 0, okay, I start from this node. Now, if the alphabet symbol I see, if the first bit of that alphabet symbol is 1, I go to here. If the first bit of that alphabet symbol is 0, I go here. All right? So now if I'm here, I look at the second bit of the alphabet symbol. If it's 1, I go here. If it's 0, I go all the way here. And now I know that the next state is 2. Okay? So I basically feed the bits of the alphabet symbols to the BDD, and it tells me which one is the next state once I feed all the bits. Now, why use this? Because it's more compact than this. This I have to put all the transitions, for each alphabet symbol. This is a very compact representation. So this actually typically has less number of states, and we save memory. Okay, so now there is another thing that I need to mention. So if I have a program like this, okay, what I said so far works. But this program has a very particular property that makes it work. It doesn't have any loops, okay? So if I have loops, the things get a little bit more complicated because I can't just propagate this automata through the control flow graph or the dependency graph and get the constraint at the end for the sync node. So what I need to do is I need to kind of iterate over the loops, okay? So to do that, we use Automata Widening. Widening is an over-approximation technique. When you have loops, you may keep iterating forever in general. It's not guaranteed that when you have a loop, you can precisely compute what the reachable states are. So widening is a technique to approximate it. So for example, I'll just give you a simple code example here. Assume we have a code like this where I have a variable. I initially assign this head as string constant to it. So then I get to a loop, and I keep, appending this tail, like concatenating this tail part, right? Now, if I just keep iterating in my dependency graph through this, I won't converge. What I want to get is actually this, at this program point 6, I want to get head, tail, clean closure, head, tail, star, right? So you won't converge to this by iteration. So you need to use some kind of approximation to reach that. So automata widening operation we have is actually, I'll just show it on this by magically. If you give two automata like this, notice that this automata is AB, and this automata accepts AB, AB. It accepts both AB and AB, AB, right? So this would be like in first iteration of the loop, maybe it accepts, I accept AB. In the second iteration, now I accept AB and AB, AB. Now, if I use this widening operator, this magic operator that we have, it actually, when you give these two iterations, it gives you this, basically AB closure, all right? So how does this magical operation work? We actually define some equivalence classes between the states of the automaton. And it's not very difficult to define. And once we have that equivalence classes, actually we generate this automaton as the result by merging states. So we have some equivalence definition. Based on that equivalence classes, we actually merge the states. And the equivalence classes we get for this two example is 0, 0. All these states are equivalent, so we merge them all here. And then these three end up being equivalent, and we merge all of them here, and then we get that automaton at the end. All right. Okay, so I talked about the forward analysis. Now, we also do a backward analysis. So in forward analysis, I told you that we used, post image. So when we have an operation, we figure out what's the, result of that operation. So in the backward analysis, we go backwards. And instead of the post, we do precondition of the statement. So we are going backwards, okay? And for this, we have to do everything again, like concatenation operation or replace operation. We have to figure out how to go backwards. So we have implementations of those. So starting at the sync now, right, we can go all the way back to the user input. So we can figure out what inputs cause the, the vulnerability. So notice that a big part of the control flow graph or dependency graph are not related to this, right? We only want to propagate the thing back to the user input, okay? So we don't care about this part of the stuff. So what we start from here, the sync, and we basically do the precondition computations and get the backward analysis results as I'm propagating here. I'm just showing you the regular expressions. Once we propagate everything back, the result we get here is what we call the vulnerability signature, okay? And that is the characterization of all inputs that violate the, that can cause the vulnerability, all right? So now there's one thing cool about this. So now I have this automaton in our format that, I know. So now the question is, can we fix the program? So this was the thing, second phase of after we did all this work on vulnerability signature generation and stuff. So we are kind of like, well, maybe now we can fix the program, right? And this actually, there is a nice way of doing that using vulnerability signature. So that's the part I want to talk about now. So in general, so now I will talk about the general thing, that the high level view. So you can think of the attack pattern as a policy specification, okay? So I have my string analysis, I have my policy specification, and I check the conformance to the policy. If there is conformance to the policy, I say everything is good. If no, I say there is a, here's an attack, possible attack. Here is actually a violation because I have vulnerability signature. I can even give you an example, right? Now the question is, after that, can I generate a patch, right? So it's a problem. Just as a side note, I want to mention that we even saw cases, this is not for vulnerability analysis, where not only that there are vulnerabilities, but there are cases where actually people reject good input. You see, I mean, that's also an error, right? So, I mean, because if you want to have a web application that's guaranteed to be not vulnerable, there's a very easy solution. Reject everything. Yeah? Reject all the user input. That's safe. But that's not what you want, right? So you want to accept certain things that are good. So typically what you have is you have a max policy, like don't accept anything outside of this, but also at least accept some stuff, right? So that's what you have. So in general, the problem is like you can either have under constraint, you accept certain things that are bad, or you can even have under constraint, over constraint, sorry, I'm saying opposite. You have under constraint, you mean that you accept stuff that you shouldn't, or you could be over constraint and you reject stuff that you shouldn't, all right? So you can actually think of it both. And the techniques I showed you can handle both. We can also actually figure out if you are rejecting things that you shouldn't be rejecting, okay? Okay, so now this is the same thing I talked about, so I'm just going to, these are different slides explaining the same stuff. So what I have shown you so far is, this is the attack pattern automaton. This is my automata I get after the result of my forward analysis. I take the intersection of the attack pattern with the result of the forward analysis, and I say that the intersection is not empty. Then I detect a bug. Then I propagate it backwards, and that's the pre-image, and I get my vulnerability signature automaton, all right? So that's what we already talked about. Now the question is, how do I fix this? So since I have this automaton that characterizes all bad inputs, first what I could do is I could put this automaton at the input, and I could just simulate it when I get a user input, all right? So when I get a user input, if it matches this, I can say, this is not good. So I could, when it matches this automaton, I could just reject it. Okay, so just reject. Okay, that's one safe way of doing it. But that is not sanitization. That's actually validation. You are rejecting something, right? You are not fixing it. Sanitization is about cleaning up. So then the more interesting thing could be is, can you sanitize this input? Actually fix it so that it's not dangerous anymore. All right. So map it to something that's actually acceptable. All right. So now how do we do that? Well, this thing accepts a string starting from the initial state and going to an accepting state. That's how the automata accept. Now, if the empty string is accepted, meaning that empty string causes a vulnerability, there isn't much I can do, right? So even the empty string is an attack, but that's typically not the case. You can't just get an attack with an empty string, typically, right? So typically what's going to happen is there will be some characters that you will need to see to attack to happen. And in this case, it's cross-site scripting, so left angle is actually the character that's causing the attack. So what I need to do is kind of delete these suspicious characters. But the vulnerability signature automata actually is telling me what the suspicious characters are. It's the characters that separate the start state from the accept state. Okay? So if I can separate the start state of the automaton from the accepting states, those characters on those transitions are actually the ones that cause the problem. So we can get if we get a cut from between the start states and accepting states, those actually are the characters that cause the vulnerability. And deleting those characters would actually fix the vulnerability. So this is the automated patch technique we developed. And okay, there is one issue here. How do you get this cut? Well, there is well-known Mincut algorithm for graphs. It's polynomial time. So you can, given a set of nodes, you can say, okay, find the cut that separates these nodes from each other. And then you can do that and delete all the characters that label those transitions. So that's the way you can patch it. Now, it turns out Mincut algorithms minimize the number of edges, okay? What we actually want is not to minimize the number of edges, but the number of symbols on the edges. So if you have the same symbol on 2 transitions, that doesn't cost more, right? I want to delete as little as possible, right? So if I delete everything, that's not good. But so that one we call alphabet cut, and that's actually apparently MP complete problem. But anyway, so we used Mincut as a heuristic, okay? So we can generate patches like this. So basically, automatically, we can, so remember the faulty replace operation? Doing the analysis using the attack pattern, actually, we can generate this patch that deletes just the left angle, which is the only one that's actually causing the trouble. And then it will basically patch the user input for you. Okay, so I'll show you some experiments on this. I mean, these are a little bit old, unfortunately, but so we did a bunch of 3 applications for this one. Use this attack pattern, and then here I'm going to show you how long it takes. So one thing I want to note is, first of all, how big are these programs we are analyzing? Since we are only interested in sensitive operations, which we call sinks, we get rid of everything else. So we actually get a slice that only gives us inputs and the sensitive operations. So the number of nodes are actually pretty small. We get rid of a lot of the application, right? So it's only focusing on the sensitive operations. So it's 20 nodes or so, and then we have 1 sink each, and then we have 1 input flowing into that sink. In some cases, we have 2 inputs flowing into the same sink. And it takes less than a second to do the forward analysis. Now, backward analysis is different. So you see that backward analysis in one case takes 40 seconds. It's more expensive to propagate back. So that actually is a bottleneck in terms of execution time. And then here are the patches that we generated. So for the first program, basically, it says delete left angle. For this one, it says delete S, single quote, double quote. Some of these may coming from basically imprecision in the analysis, right? We are over approximating sometimes, and because I have the widening operation and stuff, so it's deleting more than it's necessary. I want to note that for this example, which is one program that has 2 inputs, it actually says delete everything. So this is not a good patch. So, and the reason this is happening is that the sink is getting 2 inputs, inputs from 2 places. So I can't fix it by just deleting from one of them. I need to take both of them into account, all right? So because if I ask the tool, fix this vulnerability by just, focusing on 1 input at a time. And the tool says, well, I mean, if I'm just looking at 1 input, the other input can contain the attack. So I'll just say delete everything, okay? So it doesn't give you a good result. But we have a fix for that. So we call this the relational vulnerability analysis and relational vulnerability signature. So we take into account relationships between the 2 inputs. And I'll just show you the result of this without telling you how we do it. But the key is using something we call multitrack automaton. So we use an automaton that actually recognizes multiple strings at the same time. So it's recognizing tuples of strings. So for example, on this example, if I have 2 inputs that's influence 1 sensitive function, so I have to take both of them into account. And let's say this is the attack pattern. Here is the vulnerability signature we generate. Just briefly explain what's going on here. So this automaton has 3 tracks, okay, 3 tracks. It's recognizing tuples of 3 strings. One is the first input, the other one is the second input, and the third one is the strings the strings that reach the sink, okay? So it's accepting tuples of strings. So it basically says, when input 1 is this string, input 2 is this string, this is the output string, okay? So it accepts those. And then I generate a vulnerability signature based on that, okay? And this vulnerability signature automaton now, I'll tell you what it accepts. It accepts tuples of strings where either the first one or the second one contain left angle in it. So that's the English explanation of what this thing does, all right? Otherwise, I need to give you all the math of definition, but believe me, that's what it does. And it's intuitive to see lambda is actually, we call it a padding symbol. Lambda is like empty string, okay? So what this automaton is doing is whenever it sees left angle in the first track or the second track, it accepts. You see, here it sees the left angle in the first track, it accepts. Here it sees the left angle on the second track, it accepts. Here also the second track, it accepts. So if it sees left angle on one or the second track, it accepts. Okay, so that's the constraint I want. You know, either the first input or the second input contains the bad character. So now I can do a cut on this one. Here is the cut, separating the initial state from the accepting states. And if you look at this cut, actually it's saying delete the left angle symbol from the first and second track. So now I actually get a precise cut. It's exactly what I want. And then I can do the sanitization. Now I can delete it from both tracks. And you know, I get the result I want. Okay. Now, so this is kind of the overview of this stuff we did with string analysis. Now, I have a whole another area that I won't get into the details. I'll just give you the high-level idea, and then technical stuff we can discuss if you are interested after the talk. The area we call differential string analysis. Okay, so this technique, the insight is the following: when I have a web application, I do some input validation and sanitization both on the client side and the server side, as I mentioned earlier. Okay, now, there should be some consistency between these two things, right? It's the same application. I mean, so there is one policy, I'll tell you. It's not based on attack patterns. It's not based on any policy specification. The general rule of thumb is that the server-side sanitization should always be stronger than client-side. So server-side should never allow a string if the client-side doesn't allow it. Server-side should always be stronger. Why? Because the malicious user can bypass the client side. So you cannot trust the client side sanitization. The point, so then, or validation. So then what's the point of client side validation? If you can't trust it, why do you do it? For response time. They do client side checking because they want to just be, you don't want to wait to server your request to go to the server and get rejected. If the application can do it at the client side, it tells you this is bad input, you know, try another input. But that optimization is not a safety, you know, it's not a security policy. You have to still check it in the server side. So now I have this, you know, my client side JavaScript code, and I have my server side PHP or Java code. What I want to check is, you know, when input goes through my server side code to the sink, the set of strings that are allowed there should always be a subset of set of strings that are allowed by the client side. So this is my differential check policy. And so we basically implemented this differential analysis. We get a target sanitizer and a reference sanitizer. Reference sanitizer could be the client side or the server side, depending on which one you want to do. And then we do this differential analysis. We see if one is stronger than the other one. If yes, we say, OK, good. You know. If not, then we actually say, OK, you know, there is a bug. If you want this to be stronger than, if you want target to be stronger than reference, then there is a bug. And we also generate a patch. So we can also generate a patch to fix it. All right. So this is the differential analysis framework we did. OK. So I'll now show you a little bit results on that. Because given the time, I'm thinking some results on this approach. So we applied this to several applications, you know, the differential analysis. So we did client-server client comparisons. We also did server-server client-client comparisons across applications. So one thing you can do is in the same application, you can compare the client-side check with the server-side check, or you can do server-server client-client across applications. And you get a bunch of pairs. And then we generate patches, basically. We generate fixes. If one side is stronger than the other one, we basically generate a patch that makes the other one stronger. There are different types. These are different type of patches that we generate. One could be just based on validation. There is no sanitization, basically. It's just rejecting stuff. Sanitization is when we delete stuff. And then length patch is another sub-area of this actual validation. But we generate a bunch of patches for these. And then, so the one thing to note here is, see, in this case, why is this 0? In this scenario, what we are trying to do is make the client-side sorry, make the server side as strong as the client side, okay? So increase the server side, patch the client server side based on the client side. Client side does not do sanitization typically. So we don't get any sanitization patch if we are fixing the server side based on the client side. Client side, all it does is actually validation. So we get a bunch of patches for validation, but not for sanitization. But the other way around, when we fix the client based on server, actually we would get sanitization patches. So there is a difference, there is an asymmetry between the client and server size. This is the number of characters. Remember I talked about the cut, the characters we delete. This shows you how many characters we delete in general, like 4 to 10 characters, so we are not deleting everything. We also infer not only, so for example, delete 10 characters is good, but you may want to say, for example, if it's a trim operation, what you are deleting is space. Trim actually gets rid of space from the beginning and the end. So it's better to infer that it's a trim rather than saying that delete the space, okay? Because if you delete space, then you are deleting space all around the input, right? So we have some specialized algorithms to detect that it's a trim. It's not deleting the space, it's actually trimming the space. So we have some more specialized things there. And just wanted to show you the BDD sizes we get. So we get like for some constraints that involve length, which I didn't get into, but things get big, and then you can see the execution time gets a little bit large, 168 seconds, or so it gets takes some time. So I will now close with just showing you the architecture of what we had. So one tool I talked about first is this, we call it stranger and lib stranger. So this is something, basically, we use this tool called Pixie Frontend, which is the dependency analyzer that we use. It constructs the dependency graph. We give it the sinks and the inputs, and it gives us this dependency graph. Then we have our string analyzer that uses MonaAutomata package to compute all the automata for the vulnerability signature automata and the vulnerability automaton. So that's the first tool, vulnerability analysis and the vulnerability signature generator. And then we have this differential repair tool, which actually does the differential string analysis and patch generation on reference dependency graph and the target dependency graph, and it will generate a patch. This also has all the stuff. I mean, this part is being repeated. The same, this symbolic string analysis part is the same for both tools, right? But we built also a differential repair kit on top of it. Now, this thing is a little bit old, but in 2014, they had a string constraint solver paper comparing different constraint solvers. And our string analysis solver actually was the best according to their results there. Now, we have one recent tool. I wanted to add that slide to this slide deck, but I couldn't. We also now built something called a model counting string constraint solver. And if you are interested in side channel analysis, that's something we use for side channel analysis. But that's a whole another talk, so I don't have time to go into that. But so we took this part, symbolic string analysis part, and converted to a basically string constraint solver. And it can be used for symbolic execution and can be used for side channel analysis in security. I have a long list of related work. So I can just show, I'll just go over the slides to see how much work that people have done in this area in recent years. And these are all in the last 10 years. So I can keep going on. Lots of papers in this area. And it's getting more and more work, especially string analysis area. Vulnerability analysis is one motivation, but people have found other applications for string analysis. So it is a very active area. If you're interested in, there's many work to do. And currently I'm working on writing a book actually on monograph. When I say book, it's a monograph, right? It's going to be basically mainly a research target. Maybe you can use in a graduate class or something. So anyway, I'm supposed to finish it, but I have been postponing the time. Hopefully one day I'll finish it. All right, so that's it.
Thank you very much.